Hello there. In this lesson, we're going to look at how stoichiometry can be used in situations that involve solutions. So how to do limiting reagent with solutions, how to find how much precipitate you're going to get, and ions, and so forth. So let's begin. So as you know, solutions can be involved in all sorts of reactions. We got reactions like baking soda and vinegar, where the vinegar is a solution. You have neutralization reactions, where the acids and bases are solutions. You can have reactions that produce gases. You can have reactions that produce precipitates. And so we're going to have a look at some of these situations and how the solutions and concentrations might be involved. So first of all, when you're finding your limiting reagent, this can be done in pretty much the same way that we did with masses and molar masses. You just use the volume and the molarity values to work out the moles and determine the limiting reagent that way. So let's try that out with this reaction. For reactant number 1, we have magnesium chloride, and we're going to take 30 milliliters. I'll put this into liters, right? We'll just move this over 1, 2, 3 spots. So it's 0.03 liters times 0.5 moles per liter. And we're going to end up with 0.03 times 0.5 equals 0.015 moles of magnesium chloride. And then for the other reactant here, we got silver nitrate, and we've got 0.03 liters of that. And same concentration and same volume, which means same number of moles of each. However, in order to determine which one's going to be limiting, you're going to divide by the coefficient. And since that's a 1 and that's a 2, that makes this guy your limiting reagent. The alternate way would be to use the concentration and the volume of one to figure out what volume of the other would be required, and then you compare it to the volume that you have. But I usually use this way. Now, once you know which of the reactants is the limiting reagent, well, then you can work out any number of components of the reaction. In this case, you're asked for the mass of the precipitate. So this guy here is the precipitate because it's the solid that's made. And we're going to use the silver nitrate because that one was our limiting reagent from the previous slide, because we're using the same starting quantities here. So if we want to know the mass of the silver chloride precipitate, then we can start with the 0.03 liters times the 0.50 moles per liter of the silver nitrate. And then that gives us moles, and we're going to do the mole ratio. So nice easy one there, 2 to 2. So we're going to get 2 moles of silver chloride for every 2 moles of silver nitrate. And then we just need the molar mass of the silver chloride to finish this off. I'm going to pause and look that up. Okay, so I got 143.3 grams for every mole of silver chloride. And so if we work this out, 0.03 times 0.5 times 143.3, I get 2. I guess we only got 2 sig figs here, so 2.1 grams of the precipitate. Yay! Alrighty, now what about the ions that are left over, the things that didn't precipitate? Well, first of all, we can look at spectator ions. We know that the spectator ions are going to be the ones that didn't form precipitate, so the magnesium and the nitrate here. And in order to work out their concentration, we can just treat this like a dilution, right? Because both of these ions would have started from in 30 milliliters and ended up in a total volume of 60. Okay, so let's have a look at that. We got magnesium and we've got nitrate here. So for magnesium, let's use this guy here. To find the magnesium ions, we're going to use the 0.03 liters, and it's 0.50 moles per liter, and that's moles of magnesium chloride. But if you look at that formula, there's only one there's only one magnesium in there. So 1 mole of magnesium for every 1 mole of magnesium chloride. And that'll be the moles. So we can work that out. So 0.03 times 0.5 is, there it is, 0.015 moles of magnesium. And then if you want the concentration, just divide by the total volume, which is 60 milliliters, which is 0.06 liters. So divide by 0.06 equals 0.25 moles per liter for magnesium. Let's have a look at nitrate. I think it's pretty much the same. If you have a look, you got the same starting volume, the same starting concentration. It's silver nitrate here. I don't know why I put that there. But we see that there's also 1 mole of nitrate for every 1 mole of silver nitrate. And so you're going to end up with the same number of moles. And you're going to end up with the same final volume, which means you'll end up with the same final concentration. Great. Okay, so this is probably the trickiest part, is working out the concentration of ions that were partly used up. So we took care of the spectator ions there before. Magnesium was a spectator ion, the nitrate was a spectator ion, and they just got diluted by being in the vicinity of that reaction when you're pouring 2 solutions together. The limiting reagent here was the silver nitrate, and since nitrate was a spectator ion, really it was only the silver that was the limiting part. So the silver got all used up, which means that the chlorine was part of the excess, and this was only partly used. Partly used. So that's the one that we're trying to find out here. So we're going to follow a little process to figure out how much is left over and then what concentration that would be. So first of all, you want to find out how many moles of ions did we have to start. So Cl minus to start. And so we see that the chlorine is in here. We've got 0.03 liters. It's 0.50 moles of magnesium chloride for every 1 liter. And we see that there are 2 chlorines in every 1 magnesium chloride. So that's going to give us 0.03 times 0.5 times 2 equals, and we're back to 0.03, 0.03 moles of chlorine ions. And then it says, find the moles of the ions used. So that was to start. Next, we want chlorine used. So here you have a couple options. You could work out the chlorine that's in the precipitate, or you could use the limiting reagent to go back here to work out how much is in or was used out of the other reactant. I guess I'll do that second one. You get the same answer regardless. So we're going to use that same 0.03 liters of the limiting reagent, so that's the silver nitrate. And then we're going to use the molarity, that many moles of silver nitrate for every liter. And then we use the coefficients for the mole ratio. So 2 moles of silver nitrate for every 1 mole of magnesium chloride used. And then we want chlorine ions, and there's 2 chlorines for every 1 magnesium chloride. Okay, so let's see what that works out to. So 0.03 times 0.5 divided by 2 times 2 is 0.015 moles per liter chlorine ions used. All right, so we're almost there. So chlorine ions remaining. You got to take what you started with, moles, and subtract what was used up, moles. And since that's half, we're going to end up with 0.15 moles of chlorine ions remaining. And then the concentration of chlorine ions, a little square bracket is used to indicate the concentration in moles per liter. So we'll take the 0.015 moles of chlorine ions, and we're going to divide that by the new volume, which was 60 milliliters, or 0.06 liters. And so when we do that, divided by 0.06 is 0.25 moles per liter. Yay, we did it. Alrighty, so solutions can also be involved in reactions that produce gases. And so let's use this example here where we have a solution of sodium carbonate, 20 milliliters of this concentration of sodium carbonate, that's this guy. And we want to know the volume of carbon dioxide at STP. So that guy here is a gas at STP. So what you can do is the same 3 steps that you do in any stoichiometry: convert to moles, use the ratio, and you're off to the races. So let's say volume of CO2 is what we're looking for. And we will start with the 0.020 liters of the sodium carbonate. So convert to moles first. We'll use 0.35 moles per liter from this value from the question. So that gives us moles of sodium carbonate. And then we'll use the ratio. It's a nice easy ratio, 1 to 1. So 1 mole of CO2 for every 1 mole of sodium carbonate that reacts. And then the final stage will be to figure out the volume. So since this is at STP, it's 22.4 liters of CO2 for every 1 mole. And we'll see the liters cancel out, moles of carbon dioxide cancels out, and we should be left with liters of carbon dioxide. So let's see what that works out to. 0.02 times 0.35 times 22.4 is 0.1568 liters, which isn't a lot of liters. That's like 156 milliliters, a good amount. Let's see, sig fig wise, we have 2 in our concentration there, so we'll have to say 0.16 liters is our final answer. The last type of reaction that we're going to look at that involves solutions are going to be neutralization reactions. Neutralizations involve an acid, which provides hydrogen ions or H+ ions, and then a base, which provides hydroxide ions. And then those two are going to combine and give you water. And then the remaining component is called a salt. So stoichiometry can be used to work out the quantities involved in a neutralization reaction. And you can do it just the same way that you would any other stoichiometry problem. You're just looking for volumes, and you're going to use your molarities in order to get that. So it's asking what volume of this acid here would be needed to neutralize this volume of this concentration of the base. And so we can do this just normal stoichiometry wise. We're looking for a volume of H2SO4, and we are given 0.03 liters of this base, and the concentration of this base is 0.35 moles of sodium hydroxide for every liter. So now we got our moles, then we can use our ratio, and ratio is a 2 to an invisible 1. So 2 moles of sodium hydroxide go to 1 mole of our acid, which is sulfuric acid. And then in order to get the volume, we need the concentration of that acid, and it's 0.25 moles of H2SO4 for every 1 liter of H2SO4. And so that will give us a volume, because everything else should cancel out. Okay, let's work it out. So 0.03 times 0.35 divided by 2 divided by 0.25 equals 0.021 liters, or 21 milliliters. Yay. Another thing you can do is work out whether or not your solution will be acidic or neutral or basic using the quantities that you're given from a neutralization reaction. You can do this a variety of different ways. You could work out limiting reagent, or you could work out how much of each one is needed to neutralize the other and see if there's enough there. I think I'll do the limiting reagent method just because it seems a little more straightforward to me. So you got HCl here, and it reacts with NaOH, and it's going to produce the NaCl and the water, right? And so in order to work out the limiting reagent, we take the moles, we'll start with the acid here, and then we'll do the base. So for the acid, we've got 0.025 liters times 0.1 mole of HCl per liter of HCl. And that'll come out to equals 0.0025 moles of HCl. And then we'll look at this other one here. We've got 0.03 liters of the base, and it's 0.08 moles of NaOH, the base, per liter. And I don't know why I keep putting an X. And that one I'm going to have to do with my calculator. It's 0.03 times 0.08 equals, and we've got 0.0024 moles of NaOH. So since the coefficients for both of these are 1, so you're going to get the same number, which means this is the smaller one. This is the limiting reagent, gets used up, which means there's no more of it left over. This one here is in excess, which means there's going to be some of it left over. Therefore, the remaining solution will be, drum roll please, acidic, because of the excess acid. Great, hope that helps. See you soon.